Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is session 19. In this session, characteristics of shunt and series motors, 3-point starter, and a few worked examples. These are the topics covered. So first, the characteristics of DC series motor. So first is torque versus armature current characteristics. For a series motor, field is in series with the armature. So the equation for torque is 1 by 2 pi phi z ia into P by A. So torque is proportional to flux and armature current. Here in this case, armature current, field current, main current drawn from the mains all are the same because the connection is in series. So torque is proportional to phi into Ia, but phi is proportional to Ia. This is the armature current. The flux produced by the field winding is proportional to armature current. So here all these curves are plotted assuming that till rated load the motor is not reaching saturation. Once saturation is reached, phi will remain almost constant and we can consider torque is proportional to Ia. But here we are assuming that till rated load, the saturation is not reached. So torque is proportional to phi into Ia. Since phi is proportional to Ia, torque is proportional to square of the armature current, or torque is proportional to Ia square. So the characteristics, torque versus armature current, it is shown in this figure. Because torque is proportional to square of the armature current, torque versus armature current has got this particular shape. Next, speed versus armature current. So speed is proportional to EB by phi because EB is equal to phi z and P by 60A. Other parameters are constant. So we can rewrite it as N is proportional to EB by phi. But for a series motor, back EMF is equal to V minus Ia into Ra plus Rf because field and armature, this is Rf and the resistance of armature is Ra. So back EMF is equal to V minus armature current into Ra plus Rf. So this can be neglected because the drop is relatively very less comparing with the rated voltage. The voltage drop even at full load is negligibly small, so we can take the numerator as V. This neglect this part. Comparing with V, the voltage drop is relatively very small even at full load. So this drop can be neglected and numerator can be assumed constant. So we can write the relation N is proportional to 1 by phi. Again, phi is proportional to Ia because we are assuming that till rated load, the motor is not reaching, field volts are not reaching saturation. So we can write N is proportional to 1 by Ia. So inverse relationship, speed, armature current, this is the shape of the characteristics. So note that when armature current is very small, speed goes to very high values. So this is a point to be noted. When armature current is less, somewhere here assume, then speed goes to dangerously high values. So a series motor should never be started without load. There should be some load on it, or the value of Ia should be sufficient enough to keep the speed within limits. Next, speed versus torque characteristics. Speed, armature torque. So we know that torque is proportional to square of armature current. We derived here. Torque is proportional to Ia square. But speed is proportional to 1 by Ia here. So instead of Ia, we can put square root of Ta. So speed is proportional to 1 by square root of armature current, armature torque. Speed is proportional to 1 by Ia, or speed is proportional to 1 by root Ta. So this is the shape of the characteristics. So these are the characteristics of a series motor. Now we go to shunt motor. So for shunt motor, this is the general relation. Torque is proportional to phi into Ia. But shunt motor phi is constant. Field current is constant. So once the motor is brought to rated speed, we don't do anything with the field circuit. So field current during the operation from no load to full load remains constant only. So phi is constant in this case, and torque is directly proportional to armature current. So torque versus armature current characteristics is a straight line, linear proportion. Then speed versus armature current characteristics. So we know that N is proportional to Eb by phi, and here phi is a constant, because for shunt motor the flux remains, field current remains constant, or flux is constant. So we can write N is proportional to Eb, or N is proportional to V minus IARA. So there is, when the motor is loaded from a small value to its rated value, there is slight drop in speed. So when Ia increases, N is proportional to V minus IARA. When Ia increases, IARA increases. So this value on the right hand side drops slightly. But for all practical purpose, it is considered as a constant speed motor, even though there is slight drop in speed. Next, speed versus torque characteristics. We know that the torque is proportional to Ia. So here we plotted speed versus armature current characteristics, but again torque is directly proportional to Ia. So speed versus torque characteristics is same. So speed versus armature current characteristics. It is like next 3-point starter. So what is the need of a starter? First of all, this is a shunt motor, starter for shunt motor. So we know that Eb is equal to V minus IARA, or Eb is equal to phi ZNP by 60A. So at starting, speed is equal to 0. So EB is equal to 0 at starting, at start. Again, IA is equal to V minus EB divided by RA. We know the equation EB is equal to V minus IRA. From that, we can write down this equation. IA is equal to V minus EB divided by RA. So at start, EB is equal to 0. So if we at start, since EB is equal to 0, equation for IA becomes V divided by RA. So if we take a small motor also, say 220 volt motor also, say 5 HP or something, armature resistance will be somewhere around 1 ohm or less than 1 ohm. 220 divided by 1. So armature current will get a 220 ampere, which is a very high value of current. So since speed is equal to 0 at start, back EMF will be 0, and armature current will, equation for armature current will be V divided by RA, since EB is equal to 0. So the magnitude of IA will be very high at start. So what we do is, we'll connect a resistance in series with the armature while starting, so that equation for IA, then it will be IA is equal to V divided by RA plus R at start. This is the external resistance which we are adding, so that IA is within limits. So we'll add a suitable resistance in series with the armature at start, so that armature current at start is well within limits, so that no damage is happening to the motor. And slowly this resistance is cut out and motor comes to the rated speed. So that is what is required. So accordingly, here see the circuit. This, let us mark it as L, line, F, A. These are the 3 points. It's called a 3-point starter. Line, field, armature. That means this terminal should be connected to the positive of the DC supply. Terminal F should be connected to the field winding. Terminal A should be connected to the armature of the motor. So the other terminals, AA and FF, it should be shorted and connected to the negative of the DC supply. So externally, the terminals provided L, it should be connected to the positive of the DC supply. Terminal F should be connected to the field. Terminal A should be connected to positive terminal of the armature. The negative terminals are shorted and connected to the negative of the DC supply. Now from here we will trace the connection. See, from here the connection goes like this. There is a magnet here, and from there the connection is made to the handle. This is the handle. So the handle is here, that is the motor is in off position now. Once the handle touches this particular stud, that is stud number 1, then through all these resistances, R1 plus R2 plus R3 plus R4 plus R5, it goes to the positive terminal of the armature. And like this, the circuit is completed. Another circuit, when the handle touches stud number 1, another connection, it goes like this. And it goes to another magnet. And from the magnet, it is coming to F through the field winding. The circuit is completed like this. So right now the handle is in off position. When it touches stud number 1, one circuit, That is, through all these resistances, current passes through A, through the armature, to the negative. The circuit is, one circuit is completed. Armature circuit is completed like that. And also at the same time, a parallel connection from stud number 1 comes like this through this magnet to F, to the field winding, it comes to the negative. So the moment the stud makes contact with, moment the handle makes contact with the stud number 1, two parallel circuits are completed. One through the series resistance through the armature to the negative, then another one through this magnet to field winding and then to negative. So the complete current always passes through this magnet. There are two magnets, one is here, one is here. Let's take this as M1, this is M2. So the complete current taken by the motor passes through this magnet. But the current passing through magnet M2 is the field current of the motor. See, through whatever current passes through the field, the same current only is passing through M2. This is a soft iron piece. Starting handle, this is the starting handle. This thing with the black shade is a soft iron piece. There is a spring here because the handle is to be kept in off position when the motor is not in operation. So due to the action of the spring, the handle is always in the off position. Always means when the motor is not operating, it will be in this position. Now, when the handle makes contact with the, suppose you are starting the motor, handle makes contact with the stud number 1. As I told you, through all these resistances, current passes through the armature and direct connection is made to the field. So current passes through the field winding as well as the armature winding. But across the armature, the voltage will be less because of the presence of these series resistors R1 plus R2 plus R3 plus R4 plus R5. All these resistors are coming in series with the armature. So the voltage across the armature will be less. So armature current is limited. Or the current through the armature is supply voltage divided by armature resistance plus sum of all these. This R is equal to R1 plus R2 plus R3 plus R4 plus R5. So the motor starts. Slowly the handle is moved towards right. Say, let's take some intermediate position, stud number 3. When the handle is at stud number 3, only R3, R4 and R5 are in series with the armature. Remaining is cut off. That means resistance in series with the armature is less now. Motor picks up more speed. And at the same time, see the handle is in contact with the stud number 3. See the field circuit. So from here, the current comes through the handle, then stud number 3. Through R1 and R2, the field circuit is completed. That means some resistance is inserted in series with the field winding. R1 and R2 comes in series with the field winding. That also contributes to increase in speed. So slowly the handle is moved towards right. When it is in the on position, all these resistances are cut off. Now IA is equal to V minus EB by RI. Because there is some value for back EMF now, motor is running at a certain speed. Not certain speed, it is almost full speed only. So when the resistance is completely cut out, back EMF picks up and armature current reduces within safe limits. And at the same time, when the handle is in contact with the last stud, the field circuit is completed through all these resistance. Complete resistance comes in series with the field winding. That also contributes to bring the motor to the rated speed. That means in armature circuit there is zero resistance, and field circuit some of these resistances are connected coming in series. So at this position the motor is operating at a rated speed. Now on position, what happens is that the complete field current passes through magnet M2. Through the coil of M2, the complete field current passes. This is the field current. This is the armature current. The field current is passing through the coil of M2 and the magnet is energized. There is a soft iron piece here. When the handle is here, the magnet will attract the soft iron piece, and due to that attractive force, the handle remains in the on position. Now, there are two protections provided. This is meant for overload and this is meant for no volt. So this coil is called hold on coil because when the handle is here, the soft iron piece attached to the handle is attracted by magnet M2 and it remains in that position. So it's called hold on coil. And if power goes off all of a sudden, what happens is that there is no current through M2. Supply went off. That means magnet M2 is de-energized. So what happens is that due to spring action, the handle goes to off position. So when power goes off, the handle should go to off position because if it remains in the on position and power comes back at a later stage, when power goes off, motor stops after some time and power comes back immediately after that, then the complete voltage will be applied across the armature. So when power goes off, for the protection of the motor, the handle should go to off position. So when power goes off, M2 is de-energized and due to spring action, the handle goes to off position. So protection is given against no volt condition. So this coil is called hold on coil or no volt coil. Then the magnet M1. So as I told you, the complete motor current passes through M1. So due to some reason, if current drawn by the motor goes above a limit, then what happens is that, see, this is a end piece, this will be pulled up. This will be pulled up towards this magnet and these two terminals are shorted. So during normal operating condition, so during when the motor is drawing normal current, the attractive force of magnet M1 is not sufficient to pull up this lever. There is a hinge here. The attractive force is not enough to pull up this figure, pull up this lever. But when current goes above a limit or above a preset value, the attractive force will be sufficient enough to pull this lever up. When the lever is pulled up, these 2 points are shorted. That means the terminals of M2 are shorted. That means M2 is de-energized. It goes to off position. So protection is given against overload and no volt conditions. So this is the 3-point starter used in a DC shunt motor. three terminals L, F and A. The cell connection should be given to supply positive, F to field, A to armature. The negative terminals are shorted and connected to negative of the mains. So when the stud makes contact with when the lever makes contact, handle makes contact with stud number 1, the motor starts, and the complete resistance R1 to R5 comes in series with the armature, and the full supply voltage is available across the field winding. But as the handle is brought to on position, the complete resistance is cut off from the armature circuit, so that in the armature circuit, the complete voltage is applied directly and the resistances come in series with the field winding. So this is the condition required for normal speed of the motor. Once the handle is brought to on position, due to magnetic attraction of magnetic attractive force exerted by M2 on the soft iron piece, it remains in the on position. So under no volt condition or overload condition, the magnet M2 is de-energized and the handle moves back to off position due to spring action. So the starter provides safe starting, then protection against overload, protection against no volt. We'll work out some examples. A DC shunt machine generates rated voltage of 220 volts. That means generated voltage E is equal to 220 volts on open circuit while driven at 800 rpm. So the generator is driven at 800 rpm. So it's mentioned a DC shunt machine. When it operates as a generator, it generates 220 volts at 800 rpm. Armature resistance is 0.5 ohm. R is equal to 0.5 ohm and field resistance is 220 ohm. So field current, you can take it as 220 divided by 220, 1 ampere. We will calculate it here. So now find the speed of the machine when running as a motor at 220 volts, taking 11 ampere from the main. So it's working at a 220 volt, taking 11 ampere from the mains. Field current, say field resistance is given 220 ohm. So field current is 1 ampere. So armature current is 11 minus 1, 10 ampere. So back EMF we can calculate. Applied voltage is 220 volts. Armature current is 10 ampere. Armature resistance is given, it is 0.5 ohm. EB is equal to V minus IARA. That is 220 minus 10 into 0.5. That is 250 volts. So in both the cases, here the equation for generated EMF is phi ZNP by 60A. Here for back EMF also it is phi ZNP by 60A. So we can write down the relation like this. E divided by EB. E is the generated voltage when the machine is working as a generator. EB is the back EMF when the machine is working as a motor. So E divided by EB is equal to N1 by N2. N1 is 800 rpm. E is 220 volts. EB, when the machine is working as a motor, the back EMF is 215 volts. So from this equation, speed when the machine is working as a motor is 781.8 rpm. Next, a 200 volt DC shunt motor running at 1000 rpm takes an armature current of 10 ampere. When the motor is loaded, the speed reduces to 995 rpm. Find the new value of armature current. Ra is equal to 0.4. So a 200 volt DC shunt motor runs at 1000 rpm taking an armature current of 10 ampere. When the motor is loaded, speed reduces to 995 rpm. Find the new value of armature current. So first we have to find out EB2. From EB2 we can find out the armature current in the second case because EB2 is equal to V minus Ia2 into Ra. EB1 is equal to V minus Ia1 into Ra. EB1 is equal to V minus Ia1 into Ra. V is 200 volts, Ia1 is 10 ampere, Ra is 0.4, we get it as 196 volts. So in the second case, when the motor is loaded, speed reduces to 995 rpm. So EB1 by EB2 is N1 by N2. So EB1 is 196, EB2 we have to find out. Speed in first case 1000 rpm, speed in second case 995 rpm. So from that EB2 is equal to 195 volts. Now substitute EB is equal to V minus Ia2 into Ra. EB2 195 is equal to 200 minus Ia2 into 0.4. Ia2 will get it as 12.5 ampere. So when the motor is loaded, armature current increases to 12.5 ampere and speed reduces to 995 rpm. Next example. A 220 volt DC motor on load takes an armature current of 50 ampere and runs at 750 rpm. B is 220 volt. A 220 volt DC motor on load takes an armature current of 50 ampere and runs at 750 rpm. It has armature resistance 0.25 ohm. If the shunt field flux is reduced by 10% without any change in torque, find the new speed of the motor. So, torque remains constant without any change in load torque. That means phi1 Ia1 is equal to phi2 Ia2. So torque in first case is proportional to phi1 Ia1. Torque in second case is proportional to phi2 Ia2. So we can write down this relation phi1 Ia1 is equal to phi2 Ia2. But the shunt field flux is reduced by 10%. So phi2 is equal to, in the second case, phi2 is 90% of phi1 or 0.951. So this first relationship we can write it as phi1 Ia1 is equal to phi2 is 0.951, 0.951 Ia2. Phi1, phi1 cancels. So Ia1 is equal to 0.9 Ia2. So this is the relation between these two currents. So EB1 we can find out 220 minus V minus IARA. So first case the current is 50 ampere. So 220 minus 50 into 0.25. RA is 0.25. So 207.5 volt. So IA2 we can find out. IA1 divided by 0.9. IA2 is equal to IA1 divided by 0.9. So Ia1 is 50 divided by 0.9, that is 55.55. So EB2 we can calculate. EB2 is equal to V minus IA2 into RA, or V minus IA2 is 55.55, RA 0.25, 206.11. Now using this relation, N1 by N2 is equal to EB1 by EB2 into phi2 by phi1. Normally we take EB1 by EB2 only, but here flux is also changing. It is given in question. Flux in the second case is 90% of flux in the first case. So N1 is 750. It is given in the question, 750 RPM. N2 we have to find out. EB1 and EB2 both we calculated. EB1 207.5, EB2 is 206.11 into phi2 is 0.951. It is given. So 5151 cancels off. N2 we can get it as 827.75 RPM. So that's all for this session. Thank you very much for attending this session. If you like the session, please share the video among your friends, subscribe for the channel and press the bell icon for notifications.